Welcome back. This lecture is about time series and sequential data. So here are some examples for time series problems. I have to predict the total energy consumption of a city for tomorrow based on certain inputs. For example, the weather forecast for tomorrow, temperature, precipitation, wind. Then if it's a working day, holiday, other features. For example, season, for example. It would help to also consider the energy consumption of today and maybe of yesterday as inputs. There's an added complexity if you want to predict several steps in the future. So let's say you want to predict in 2 days, 2 days ahead. Should you iterate your model for 1 day prediction, or should you train another extra model for 2 day prediction? In time series modeling, outputs and often also the inputs are real numbers, like the energy consumption. And of course, there's a huge history on time series modeling. Financial time series modeling is an important issue or application, but it also ties into system modeling and ordinary differential equations and so on. So we cover maybe special aspects which are relevant to machine learning. So it would be a huge topic to do a comprehensive exposure. So this is the DAX, and this is I guess around 2000. So there was this e-business hype, and then it dropped, and then it increased again. And if you want to trade the DAX, you might want to predict the DAX value of tomorrow. Of course, it's not easy. As you can see, it looks pretty noisy, and that might not be a time series of real interest. Although a lot of trading and other things are being automated and partially being done by neural networks, so this might not be too far from what some companies are doing, what I'm presenting here. At least it gives you some idea of the way you look at this and how you approach these type of problems. Sequence modeling is related but sort of different. So typically the input is a sequence or a sentence and a sequence of words, and the output classified the sentiment of the sentence. And obviously language has this serial component, sequential component, and it sort of has different characteristics, this problem, but they're also common issues. Or if you look at encoder-decoder modeling, like in machine translation, the encoded sequence is a sentence in one language, and the output is a sentence in another language. And in this type of sequence modeling, inputs and outputs are typically discrete. Now there's a final vocabulary, maybe very large but finite. So you're not dealing so much with continuous numbers, more with discrete entities like symbols. So we're starting with time series modeling, in particular with the NARCS model, which stands for nonlinear autoregressive models with external inputs. And it gives you, I think, the flavor of this type of modeling, hopefully. So let's say, just for concrete example, yt is a discrete time series of interest. So the time is not treated as a continuously flowing entity, but something which can be discretized. So it can be days or hours or minutes or seconds or weeks, whatever. So there's some discretization going on that you can count the time steps essentially. Then x of t is a second time step that contains information on y of t. So if the first one is the DAX, then maybe the second one would be Dow Jones, and they typically correlates if Dow Jones goes up. The next day the DAX might also go up. If the Dow Jones goes down, the DAX might also go down. And for simplicity, we assume that both are scalars, so simple numbers. But this can be also generalized to vectorial representations. And let's say the goal is to predict the next value of the time series. So if we have data until today and want to predict tomorrow. So that a time series at time t. So this is sort of our modeling assumption, is a function of previous realizations of the same time series so maybe yt is tomorrow, and then yt minus 1 would be today, and so on, yt minus t. So you might consider a finite horizon in the past. For example, the Dow Jones, or the DAX in this case, of yesterday, 2 days ago, 3 days ago. So you're also capturing some trend information. And x of t minus 1, so we only have information also from the second time series until yesterday, let's say. And then we assume some random disturbance to make it more realistic. So epsilon t is sort of added, or we assume that this is an added noise at every step. So this is also the simplest noise assumption you can make. And the solution is pretty simple. So the idea is to model this function f, which could be a nonlinear, simply by a neural network. So the true function, which depends on the past instances of the same time series and from another time series, is modeled by some parameters, and here I call them w and v. So v is from input to hidden, w is from hidden to output, so a single layer neural network. And this neural network has the same inputs as we assume this the system has. And all these inputs are assumed to be known. So now we can measure until today, essentially. And we're just trying to fit this model to the system here. And we're simply defining a cost function, and it's our well-known least squares cost function. So it's a sum over all time instances, and we're considering the difference of the prediction of our model with these inputs and the actual time series value which we observed. And so we iterate through the time steps here. We take the squared error and we are minimizing the parameters to give a good prediction. So if you understand it, if you get the point, it's quite simple and quite an immediate generalization of what we have done before. You just have to get used to the fact that the inputs are not some measurements on some entities or something. They are realizations of the same time series and maybe another time series from the past to predict the next one. So for Dow Jones and the DAX, of course, for example, the good prediction for tomorrow would be the same value as today. But then if you capture more of the past information and more of another time series information, you might get better predictions. So it's really the same thing as before. Again, nothing much has changed. We can do simple backpropagation. We have inputs and outputs if all these things are known. So of course we don't know the value of tomorrow, but in the training data we are going to past values, and then we observe the time series for a certain time, and then we have for these past instances we have inputs and outputs. And yeah, this is called NARCs. So N is for nonlinear. Autoregressive means that we are predicting the time series based on its own values in the past, autoregressive, and external X is for external inputs, which would be this X of t. In neural networks, sometimes this architecture is also called TDNN for time delay neural networks. And note that there's this convolutional idea here that we are sort of shifting the same model over time. So similar to how we shifted the kernel in convolutional neural networks, here we are shifting this sort of same pattern in time. Okay, and after training, our prediction is quite straightforward. It's we simply put the inputs as inputs to the neural network, so the previous instances of the same time series and maybe previous realizations of another time series, and the output of the neural network is simply our prediction. So one issue, so that's I mean typically in time series problems you do some pre-processing, like maybe subtract the mean, maybe first analyze simple trends or seasonal effects, but otherwise this is quite a realistic model. One issue is if you want to predict several time steps in the future. So here it's from t-1 is available, but we want to predict maybe tau steps into the future. And maybe this is variable, maybe not. And this is quite interesting in simulation because sometimes people do have quite sophisticated models in time series based on physical principles and the like, but it's very expensive to iterate them at the time scale and the speed you want to do in real time. Now, for example, if you have a robot with many axes and you want to predict its movement, maybe you have to solve complicated coupled ordinary differential equation, and this iterative computing might be too slow to use it in real time. But you want to predict maybe in real time what will happen. And so this direct prediction, as indicated here, is quite useful in these environments. So the training is offline. You have a simulation. You train your neural network to copy the simulation, but you don't train it to predict one step ahead, but maybe 10 or 100 time steps ahead, and then your controller or your robot can use that information for better action. So that's one option, and the other one is sort of to do the one-step prediction and to iterate that in the future. So maybe you want to iterate your model, but in our situation, you would need two predictive models, one for the future value of your input time series, because that's also evolving in time. And then you have the old model, which is trained in the way before. So we have these two models. And if we have, and then if you want to do a prediction several times ahead into the future, we can sort of simulate data according to these models. So, so a future, I mean, a predicted y of t would become the input. So we can one approach would be to simply iterate the model, but then you don't take into account the uncertainty because we have this additive noise. So what you can actually do is to iterate this model, but always also add this noise to the simulation. And if you do that, you're not just predicting some sort of mean value in the future, but you also can look at the uncertainty in your prediction if you repeatedly do this forward sampling. And you get also an estimate of your uncertainty, of nonlinear effects and so on, because we are considering here nonlinear time series, which means that the prediction here is a nonlinear function of the past inputs. And this approach is called Monte Carlo simulations. And there are also, let's say, cheaper or more deterministic approximations. But Monte Carlo, I mean, in this way, it's just the time series prediction problem is not that difficult to apply. But this is, I mean, just to give you also a flavor of how you make this maybe more realistic, or in this case, how to iterate the model into the future. No? Of course, if X also has a noise driven noise source here, then you would also have to model that. And then, of course, there are a lot of hyperparameters, so what's the amplitude of this noise and so on. But if you do this Monte Carlo integration, you get quite interesting features about your prediction, and not just the mean or the expected value, but also the uncertainty in your prediction. So if we now look at sequences of words, there's the problem how you represent a word as an input to a neural network. I mean, numbers we have encountered this. I mean, scalars in time series modeling, or binary inputs, maybe 0, 1. But what do you do with a word? No? And so we assume that there are NW different words in our vocabulary, and W might be quite large, maybe 10,000 or so. And there are different options. So the first one is called one-hot encoding. So one input at a certain location in the sequence, xt, is represented by NW neurons, so maybe 10,000 neurons. And neuron I, so the ith neuron out of these 10,000, has activity 1, and all others have activity 0. So this would encode word WI in your vocabulary. We can use a similar encoding for an output, using, for example, a softmax transfer function at the output with a corresponding cost function. And for the output, this is actually quite common. For the input, we typically do something smarter. And that's called embedding encoding. So instead of representing the word as an index in some sense, we present a word by attributes describing that word. So in this notation, it's this vector a sub I describes word I. So instead of having to represent this word, we have to represent these attributes of these words. And they can be quite large, maybe 200 dimensional or so. And the question is, where do you get them from? No? So one idea might be to sort of find some way of describing words, like in some ontology, for example. So is it a living being? Is it a dog? Is it a building? Is it a so on? But the modern approach is simply to learn these embedding vectors based on a large corpus of sentences, for example. And so these AIs, they don't have a clear semantic meaning. I mean, you can sort of cluster them and analyze them and visualize them, and then you discover that there's some structure in these embeddings. But in the first step, we don't assume that there's any specific structure in these numbers. So it's just a vector of length r. And so this is version B, and version C is essentially a combination of both. So let's maybe look at the picture. This would be version A. And so here we see the one-hot encoding. So in this case, we have just 4 words, and word number 3 is the one we want to encode. And so in reality, we need maybe 10,000 of these encoding neurons. We have this one-hot encoding. And then we learn this W matrix from this encoding vector to the first hidden layer of your neural network. So the neural network continues upwards, and we call this W. So this is normal, trained like in any other neural network. Of course, we have like an explosion in representation sometimes. Now, as I said, for 10,000 words, we need 10,000 one-hot encoding neurons. And if you want to encode several words in a sequence, we have to multiply it by the length of the sequence. So this can be quite awkward. But sometimes, in some applications, we are actually doing that. And the other approach I have discussed is that from somewhere we get this attribute vector AI describing word number I, so WI. And this and this is now the input to our neural network, and we are then learning in the first step here in the neural network the map of this representation to the hidden layer, and we call this W tilde. So this is the map from this stored vector from somewhere. And so actually these people are publishing these word representation vectors, and you can download them and use them in your application as is, or you fine-tune them for your particular application, because maybe the characteristics of your application is not completely represented in these dictionary representations, and you want to fine-tune them. And this vector now from this input of this dictionary to the hidden layer we call W tilde. And we can combine these two ideas. I mean, this is more like a conceptual way of looking at that. So we keep this one-hot encoding for the words, and then this this A matrix, which consists of all these word embeddings, is hidden in this connection between these one-hot encoded inputs and this A layer of latent representations, and this one is then mapped to the first hidden layer in your neural network. So I find this more intuitive, because if we want to learn this or adapt these embeddings here, it simply means doing back propagation to the structure where these A's now appear in this connection matrix. And otherwise this looks a little bit strange that we adapt some inputs. It's sort of the same thing. It's just I find the right display, or the way to think of this in this right figure more intuitive or more easy to deal with if you want to think about how you adapt these latent representations. And if we have these, so then the question might be, what is this thing here? From the input one-hot encoding to the first hidden layer. It's sort of the product of both, no? Of a matrix which represents this latent this embedding vector and or embedding matrix and this W tilde, because we are executing them in a sequence, and typically there's no nonlinearity, so we can just multiply these two matrices. And we can use this idea immediately to train so-called language models. So a language model is a model which is able to predict the next word out of a vocabulary of NW words in a text based on the last T words. So consider that we want to predict YT, then Y sub T has NW components, one for each word. So for the output we are using one-hot encoding. The inputs to the model are parsed words, and the model assumption is that word I is associated with an embedding vector AI of dimension R. So this is the embedding representation. Thus, in the first step, a one-hot encoding word I is mapped to the embedding vector of word AI, which is then input to the neural network. And then the task is to predict the next word. And this is encoded as a softmax. So we have softmax with k dimensions, because we have with NW dimensions. And the prediction for that the next word is word k is a softmax evaluated at k, and the input here is the predicted function. So it might be, let's first look at the figure, because before we discuss more general cases. So this is the output. We want to predict, for example, the probability that WT is word I, given the context. So this would be the next word in the sentence. And in the input, now we have the embedding vectors. So here they use the letter C, we used A, of the previous words in the sentence. So T minus 1, T minus 2, until T minus N plus 1. And here it's also indicated that this can be realized by a one-hot encoding of an index, and then we would have this what they call table lookup, this A matrix in between here. So this is the word, the mapping of the word to its latent representation, and this can be adapted. In this case, then here we have so this forms the first, the input layer. Then everything is mapped to a first hidden layer, in this case the tanh transfer function. And then this is then mapped to these, let's say, 10,000 output neurons, which are combined with the softmax cost function. And the purpose of this model is not so much to predict the next word. It is to get to train these representations here, because you do backprop through this to these layers, and then also update the latent representations, which are represented as this matrix from input to this layer over here. So the purpose of this model is to get to learn these representations, which you then use maybe in other applications. Because predicting the next word in a sentence is not such an interesting application. But it's good for for training these models, because you don't need anybody to label anything. No? The words are in the text, so you can... oh yeah, that's also, I should have mentioned in the first part on time series modeling, that's what people sometimes call self-supervised learning, because you just have a time series, and since the output and input both occur, so if you have the input, you from a past time series, you have the next time step. So no human labeler is involved. So that's called self-supervised learning. And here it's the same thing. You just can use a huge amount of text data, a huge corpus, and train this model on this corpus. And you don't need to involve any persons because the words are just there. Yeah, and these latent representations are actually published, and they are like modern forms of this approach. Have these nice names like Elmo and Bert and Word2Vec and Glove. So I think Word2Vec was relatively maybe the first one in this direction. And I mean the model I showed you was even earlier. It was from a Benjo model, which was quite Joshua Benjo, which was quite a breakthrough. And then these are more modern versions of this. And this idea of learning embeddings for discrete or symbolic inputs is one of the really important building blocks of modern deep learning. So now let's look at recurrent neural networks. They are quite powerful for sequence modeling, and in the simplest way, or in the simplest form, they're used to improve the prediction by providing a memory for previous inputs. So one thing which might not have been so elegant in what we have discussed before, we need to define like a finite past time window. So in time series modeling, there was some past window in time we represented, and also in the language model we have presented. But sometimes maybe an event far in the back, in the past, has an influence. But let's first look at a regular feed-forward neural network where we don't have that effect. So we just have different prediction problems at different instances. So we just say, okay, a pattern also has a time index. And we have an input, a hidden layer, and an output. So this is just a regular neural network, and since we have different situations, so a t plus 1, and t plus 2, but currently they're just indices. So again, we have an input, a hidden layer, an output, an input, a hidden layer, an output. And in this situation, which is sometimes called IID, for independently identically distributed, you can change the order of these patterns and not much changes, because it's a data set, and we can train this, consider this maybe as a training set, and then we train on this data set, and if you change the order of these data points, it doesn't really change anything. So the idea in a recurrent neural network in this representation is that the hidden layer also receives input from the hidden layer of the previous time step. And the hidden layer now has a memory function reflecting hidden inputs from or reflecting inputs by hidden variables, really. And in terms of system theory, the recurrent neural network is a nonlinear state space model, because it contains an idea of a state of the world. So here's the example. So we have this old structure, an input, hidden output, input, hidden output, input, hidden output. But now the hidden layer also receives information from the previous hidden layer. So we have these feed-forward connections, they are called, from this hidden layer to the next hidden layer. And we have here an additional connection matrix, which we call B. So this one was the V, from input to hidden, from hidden to output. Let's say this is just one output, so it's a vector W. And in between the hidden layers, we have this new matrix B, which occurs here, 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 and here. And by having that, I mean, any hidden layer or any neuron in a hidden layer later in time, if it is influenced or can be influenced by all the previous inputs, because there's a path from here to here to here to this input, and even further back. So by this recurrent neural network structure, we introduce a memory function in our model, and we don't have to specify, let's say, how long this memory has to be. So that's also learned when we do the adaptation in this model. So in a compact notation, we can write the latent vector. So we call this ZT, is, let's say, a sigmoid applied. So this would be the input, input to Z with our normal connection matrix V. But then we consider also the previous activation of the previous hidden layer ZT-1 as an input with another connection matrix B. And then the output is calculated as before. So yeah, okay, here in this case, it's also considered to be a vector. So then this W is also a vector. We have several outputs. And this is how we... So the real new thing is that we have this connection to the previous hidden layer. Of course, the sigmoid can be tan H or something else. So the Z of T is a representation of the state of the system, a patient, a plant, whatever, at time T. Xt can also be an embedding vector of a thing which is present or active at times T, for example, a word or a medication. So a medication is the same thing, problem as a word. It's you have to transform it into a representation vector, and then you can deal with it. And we can definitely, I mean, of course, we can also concatenate different inputs, which would then be the link to representation learning. But I think this is maybe a little bit complex now. So let's consider this again. Now we have inputs. The inputs might be latent representations, embedding vectors. And then they're mapped to these blue nodes, and we are proceeding in time. You can also draw this slightly differently, but yeah, I think it doesn't give you as much insight. But sometimes you draw it more in this way, that you have this one neural network with this feed-forward character from X to hidden to out. And you indicate that there are these recurrent connections in this way. So you sort of take out this time evolution or the unfolding in time, and this makes it clearer maybe that there are recurrent connections. But it's difficult to draw, as you can see. So I think the unfolded version gives you more insight into the structure of the problem. Yeah, how can we train this? So we know how to train this. This is simply backpropagation. Here's the error, and then we propagate it back in the direction of the input, each for each pattern. But what do we do when we have this unfolded system? I mean, essentially it's the same thing, the same principle. So if we have an error here occurring at t+1, then this error is used to adapt this connection here, and this so from input to hidden and from hidden to out. but we also propagate the errors to the previous layer, which then also adapts the input to hidden here and the B matrix, and we backpropagate even further. And every time we get an error signal to adapt, so there's some sharing of parameters. No? The B and B and B is everywhere, the V is everywhere. So in other words, we are doing the same style of backpropagation, but not just within one time step. No, we also propagate backwards in time. And that's where this approach has its name from. It's called backpropagation in time. And the principle is exactly that. Writing down these equations is a little bit involved and doesn't really help much, so I left it out. But that's how you do it. Now you perform backpropagation through time, or BPTT, which is the application of backpropagation stochastic gradient descent to the unfolded network structure. You don't always do it until the beginning of time, so maybe also consider a finite window in the learning procedure. But then when you run the system, you just iterate forward in time. Yeah, so one typically truncates the gradient calculation. So this is like a big milestone, and so this was already done in the early 90s, but at that time the computers were not so fast. We didn't have so many problems of this sort, and it was sort of a community on its own a little bit, and people within this community thought this is an amazingly great thing. People outside were always a little bit skeptical about the results. I mean, this is now completely different. Everybody knows that recurrent neural networks actually work. But that also came with a huge successes in deep learning. So much later than the visionaries already knew it. And personally, for me, my belief in recurrent neural networks was born by this architecture called EchoState network. Also, it came out of the understanding that recurrent neural networks are difficult to train. So you might already have this feeling like maybe backpropagation is difficult because you have to have learning rates and convergence issue, and if you go backwards in time, these problems become even more severe. And so in these EchoState networks, which is an example of ESN, also called EchoState neural networks is ESN, and the wider family is called reservoir computing, and another instance is so-called liquid state machines. So the idea is surprisingly simple, and it's more surprising that it works quite well. So here we have an input layer. So think of this as x of t. So this is changing in time, and then this is the connection from input to hidden. And these are all the hidden units drawn in this a little bit different way, not unfolded in time, but with these recurrent connections here. And there are all sorts of wild internal weights, so our W's here. And this is evolving in time. So at first it might look like our normal recurrent neural network. And in a way it is. No? But the amazing thing is that the W's, the B's and the V's are not trained. They are simply initialized with random numbers according to some specific recipe, like how they are distributed, but they're random. Now, okay, in recurrent neural networks we also do this. we randomly initialize these weights. But the new thing is that they never adapt these weights. No, they initialize V and B, and just leave them random as they are. They never change them. And the only thing which is adapted based on the output signal is this W matrix, or W vector, depending if this has several dimensions or not. So, and this is, of course, extremely simple to train. This is just a linear regression model with one output, and the inputs are all these hidden neurons here. So the architecture is not so amazing. It's a recurrent neural network architecture. The thing is that you get quite good results without even adapting these the B matrix and the V matrix. And this is quite amazing. I mean, you don't get the best possible results. But at that time, when this was invented, as I said, it was quite difficult to train recurrent neural networks. And this was sort of very simple, very straightforward, easy to implement, and quite powerful. And at that time, they even developed special hardware chips to implement this. And I think there are some applications in signal processing, adaptive signal processing. There are also in adaptive signal processing. Now you have to learn something continuously in time, and adapting these output weights. It's sort of an add-a-line learning rule that can be done pretty robustly, and these hidden connections you never have to adapt. So your online learning systems can be quite stable. And that personally, that brought for me the belief that recurrent neural networks might be something interesting after all, because this robust and simple implementation really worked quite well. So you should also think, I mean, before we talked about time series modeling, and there we introduced this noise because you always think there's maybe some noise in the system. Recurrent neural networks don't have this noise. So if you look at this, the only uncertainty is on the output. So maybe you can model some output noise here, but there's no noise here in all these processing steps from green to blue. So it is a deterministic system in terms of the inputs. So, and even if you would have a measurement, maybe you use this as a prediction model, and then maybe you get the measurement, it would not immediately influence your prediction. It would influence your error signal for the backpropagation step, but you couldn't use this information directly to update maybe your beliefs in the states, because it is a deterministic system, and this is not considered in these type of models. Yeah, this is what I'm discussing here. And this is in contrast to other sequential models. For example, the classical models before the time of neural networks, for example, are hidden Markov models or Kalman filters or stochastic state space model, which also have a probabilistic component in these transition matrices. So you can think of this as a hidden Markov model or a Kalman filter model if you allow for noise in these transition matrices. Of course, Kalman filters assume sort of Gaussian distributions, and hidden Markov model assumes sort of you have always these one hot representations in the hidden layer. And no nonlinearities. Oh no, it's not true. They are state transitions, so they have these transition matrices. But of course, this is not a lecture on hidden Markov models, just to point to some related approaches. In some applications, you're not interested in predicting something, but maybe in labeling something. So, for example, the output might be a label to a word, you want to get. No? And in this case, I mean, you have the whole sentence. You can go into the future, but you can also go from the future to the past because the whole sentence is available. In this situation, bidirectional RNNs have been quite successful. So let's look maybe at the figure. So here is xt plus 1, xt plus 2, xt plus 3. Here we have our predictions, y of t plus 1, y of t plus 2, and y of t plus 3. And what we discussed before was this forward propagation, a forward model. That we predicted the latest dates, and then with the b, so f is now for forward, we went forward in time. And here in these bidirectional models, you're also propagating or predicting backwards in time. So you have this hidden unit here again, which is sort of different activation than this one. And you're predicting backwards in time. And then for the labeling, you're using both these latent representations, one from the forward direction, one from the backward direction. So you have twice as many latent representations here. And then you're modeling the mapping from these combined latent representations to the output. And if you can do that, so if you don't need to do a time series prediction problem, and you do a labeling problem, then this can really become much better. There's a lot of improvement here. So here it's sort of indicated. Now one is from backward in time and one is from forward in time. You have different matrices here to be trained, and then the mapping from the latent representation, which is a concatenation of these two z vectors, to the output is then trained in one way here. So now let's look at the LSTM. LSTM stands for long short-term memory. So the recurrent neural networks have a memory, but it's sometimes difficult to remember important information which occurred further in the past. So this could be remembered, but if you train it to do that, some numbers become very critical and difficult to train and are very sensitive to small errors in the parameters. The keyword people are using here is called the vanishing gradient problem. So the intuition is if you do backpropagation through these different layers, the influence on the different layers before or on the parameters which many steps in the past is sort of getting less and less. And so the key approach here is called long short-term memory. So this was invented by Sepp Hochreiter and Jürgen Schmidhuber. And another version, it's not a modern, it's just an alternative, is called GRUs, gated recurrent units. The GRUs are sort of an attempt to make LSTM simpler because, as we will discuss now, LSTMs are quite complex. And I can try to make it plausible, but I cannot say that I completely understand why it gives such a good performance. Yeah. So let's first, I try to do it step by step. So let's first look at a feed-forward neural network with a little bit different characteristics. So here we have X, the input. We have input to hidden connection where it's V, and then we apply sigmoid, and then we get our S of t. So this would be our mapping from input to hidden, quite normal. Then the first a little bit odd thing is that we apply a second transfer function, the ton-h. So essentially we have ton-h applied to sigmoid applied to vxt. And then we have a normal output layer from zt to our prediction vector y of t. So we have this a little bit strange transfer function in the hidden layer from ton-h and sigmoid both applied to vx transposed. And these things have names. So s of t, so this guy here is called the cell state vector, and z of t is the output vector of this LSTM unit, not of the neural network, which would be, of course, y of t. But that's, I mean, we have to keep to the standard way of naming things. So this is called output vector. So each of the latent units in the recurrent neural networks now become LSTM units. Thus, if we have h hidden units, now we have h LSTM units in the network. And now, so the first important thing is, or the next important thing is that in the LSTM we have these so-called gates, and there are many of them. And let's look at two of them, the input gate and the output gate. So here, so we had before the map from x to s of t, and now we're multiplying the sigmoid to the input element-wise. So this is a symbol here. So we have g of t is a vector of the same dimension as the hidden layer, and this is not a matrix, a vector-vector product or something. It means that element-wise we multiply each dimension here with each dimension here. So this is the input gate vector, and then we have the output gate vector, which is applied to the ton-h transfer function. So we have g of t and q of t, and they are element-wise products always. And the output is then calculated at before. So if the gates are all 1, which means they're all on, then we have things as before. And if a G component is 0, then this neuron essentially disappears from the network. And similar here, if Q of t of one dimension is 0, then this dimension disappears from the network. And these gates, they are also functions of the inputs. So this the propagation to the hidden layer is a function of the input, but also these gates are also so they have their own weight vectors here, Vg and Vq, but they're also calculated sort of as a hidden layer in a neural network. So yeah, let's not talk about the mixture of experts. But yeah, this sort of gating idea was not 100% new, but the way they applied it here was quite innovative, definitely. And the next thing is, of course, we want to have a recurrent neural network, and so we apply our recurrent connection here from the last hidden layer in this form. And here we connect it to the Z layer multiplied by the B connection weight. And then here we have the gate again. And I guess here nothing has changed. And the input gate and the output gate also become recurrent. So we have VG and BG, and so also the gating networks or the gates themselves have a recurrent structure now. And I think this is the last thing. We add a self-recurrency to the cell state vector. So that sort of means that the cell so we have a lot of inertia in this S of t representation. So this is what we had before, this gating network applied to the sigmoid. And now we also consider that S of t is similar to S of t minus 1 with another gate here, which is called the forget gate, which of course also depends on the inputs and has a recurrent structure. So here's another gate. So if these gates are all 0, then it is what we had before. If it's 1, then the S of t sort of doesn't, it's sort of the old one plus some change to the old one. So let's maybe first look. So this is one LSTM block, which means one neuron in the hidden layer. And this is how it can be drawn. We have all these different gates, and they all depend on the inputs and on some recurrent structure. So this is the input gate. This is a gate here. They call it sigma. This is just the input applied with a nonlinearity here at the hidden layer. Here's the forget gate. Here's the output gate. Here's the tan h. Here's the sigmoid. Here's this forgetting function. And here's some, forget about these blue arrows. It looks quite complicated, and it is quite complicated. And I think initially when this was invented and proposed, that's what people thought. Much too complicated, can never work. But then it worked, and it gave really, really good results. Maybe it's one of the, maybe it's even the first really, really complex architecture where people sort of lost control about how these things really work. But if you apply backpropagation in time and train it, it can give you really good results. Because it has these gating things which can turn things on and off, and it has this recurrent structure here, this one which is quite important to give you long-term memory effects. But you have always these individual time constants, so it's not like everything has to have this long memory. You can mix short-term and long-term effects, and it gives you a lot of complexity. And you can also think of deriving the backpropagation rules. Would be, at that time we didn't have all these modern ways of calculating derivatives automatically. At that time, you had to do it by hand, and there were so many errors you could do. So it was quite complex and involved, but the performance was really superior, and still is superior, and it's still used in a lot of applications. So here I try to motivate the example. So if something happened a long time ago, but it might have been an important information that Siemens-Stock is labeled as by, then you would have to carry this information through your recurrent neural network, which might be very difficult because you have to have some memory which is maintained for a very long time in the system. Of course, you could always have some extra input which sort of has this memory effect, but the LSTM does all that for you in a very flexible manner, and you don't have to do too much thinking. You can blindly apply this architecture and you get very good results. So So at that time, I mean, or let's say a couple years later, it was very successfully applied. I think it was invented around 2000 or something. Very successfully applied for reading handwritten text, and is even nowadays the basis for many applications involving sequential data. But LSTM is just, you can think of it as one recurrent node in a recurrent neural network. So you have several ones of them. So this is my point here. You simply replace these latent nodes here by a whole LSTM, which has a lot of internal nodes itself. But that's the way to look at them. So here it's a quote from Wiki. LSTM achieved the best known results in unsegmented connected handwritten recognition, and in 2009 won the ICDAR handwritten competition. LSTM networks have also been used for automatic speech recognition and were a major component of a network that in 2013 achieved a record 17.7% phoneme error rate on the classic timid natural speech data set. And they're used in a lot of applications like robot control, time series prediction, speech recognition, rhythm learning, music composition, grammar learning, handwriting recognition, human action recognition, protein homology detection. So something which does not work as well is transfer learning. That's one reason why the transformer and attention mechanisms became more popular recently. So one comment I read is they still work great, but for every particular application you have to train it from scratch again. And in the modern times, you want to have something where you can get a good initial starting point from, as I said, for example, embeddings and so on, which you might have only to fine tune, and you don't have to learn every model from scratch. So now we're looking at the encoder-decoder networks for machine translation, where LSTMs are heavily used. So this is about you put in a sentence in one language and you get it out in another language. One of the really big milestones and successes of deep neural networks. So this might be true a couple of years ago. So maybe now with the current thing people are using is called transformer networks, but let's recover them later. So a couple of years ago, at least, most machine translation systems rely on the encoder-decoder approach. For example, in neural machine translation, NMT. And the typical embedding numbers are rank is 1000, and so the input words are represented by a vector of length 1000, and also 1000 is the number of hidden units per layer. So just to give you some understanding. And you have to also in machine translation, people tried it rule-based, people tried it pattern-based, many different ways. A lot of insight into the problem was required, and so this is one of the examples where deep learning sort of replaced the insights. Now you can, as we discussed before, deep learning you can apply to raw data, and you don't have to do a lot of fancy pre-processing or feature engineering, and this is also true for this application. So this is how it looks like. So you put your sentence here at the input. So I am a student, and what you want to get out is je suis étudiant. So this is English to French. And so here you see the words which are encoded by embedding vectors. So it's not y, it's the embedding vector of I, of M, of A, of student. Then this blue box here represents 1000 LSTM units. So this is really a recurrent neural network unfolded in time. Here's a second layer of 1000 LSTM units. So sometimes you're using several of these layers, but the recurrent connection is then only within each layer. And so this is sort of an LSTM recurrent neural network, but no outputs. So there's no output vector or output label here. And then this is simply fed into the decoder, which has the same architecture here. And here on the decoder, so here on the left side in the encoder we have inputs but no outputs. In the decoder we only have outputs but no inputs. And the outputs are the words or the word indices in French. So here the output representing je would be active, here suis and here étudiant. And then here's also an end of sentence, so the system knows when the sentence has ended. So if you run your system, you implement your input sequence in this recurrent structure here, and then you let it decode. And the translation between both is really the embedding vector of these two constructs here. Because this information is the only one which is transformed to the decoder, which I think is quite amazing. That this works. LSTMs are of course required because you have you need these long-term memory effects, because maybe a word in the beginning of the sentence ends up at the end of the sentence, because different languages have different sentence structures. Also, what you're seeing here, you see here, je suis étudiant, but you also see this sentence here again, and that has a reason. So in a way, the output here becomes the input here. Or let's put it this way, in training, we predict je, and then je is also represented as an input in the next iteration step to the decoder. So this information, which in these structures, as we discussed before, doesn't really affect future states, but by putting this output as an input. So in training, of course, this is known, je suis étudiant, je suis étudiant. We also tell the decoder about previously decoded words. And this is during training, and during testing you have to do something similar. And there are different versions of that. You want to not just maybe put the most likely word here at the input that doesn't reflect the uncertainty. You are doing some optimization in the decoded sequence by doing some fancy beam search to finding, because you're interested in the whole output sentence, not that in a sequence of likely words. So the output is presented as input. Also in the decoding phase, and when you use it, not just in the training phase, and so the words you have predicted, but several of them are considered as option as an input here in the next time step. So this architecture sort of makes sense, but again, the most amazing thing for me is that it really works and gives you such a really good performance. Yeah, the encoder is in recurrent neural networks, often an LSTM with no output layer, but maybe several layers of recurrent units. And the encoder vectors are the last hidden states. So here's the translation from the encoder to the decoder only by these connections here and by the information flow from blue to red. And also it knows when the sentence ends. I mean, all these things are, I mean, we're slowly getting used to that these things work, but this is, I mean, it's quite amazing that this all can work by extensive training and backpropagation. And without really having an understanding of the meaning. Of course, sometimes that is criticized by some people that that they don't have any really understanding what they're translating and if it semantically makes sense. But it's simply the best performing approach. And I mean, nobody would mind if you come up with something better. So the initial later state of the decoder is the encoder vectors, and in the simplest form, so just as a recurrent neural network, we have this structure here, and in training, as I said, the input and output are the same, just with a time delay. So here this acts as an output, here it acts as an input, and in prediction, when you're using the model, you're doing some beam search, analyzing different options. Because the predicted words also appear as inputs, and there you want to be allow for some flexibility, that maybe your best prediction for initially that this was J, maybe later you want to revise and give it a different word meaning or translation, because the later words don't fit to this interpretation, and this is done by doing a beam search over possible interpretations of the sentence. Yeah, and these neural machine translation systems achieve state-of-the-art performance in large-scale translation tasks such as English to French. It has the ability to generalize well to very long sentences, and it simplified everything. I mean, it made maybe training more complicated, and maybe there you need to have some engineering insights, but before you needed these giant or gigantic phrase tables and language models, as in the case of standard machine translation. And also NMT has a small memory footprint. Although the model itself is quite big, it's still much smaller than the approaches which we used before. Yeah, and the implementation, in a way, it's much simpler, because before you needed to have a lot of insight and many years of optimization to get this right. So now let's talk about attention. It's sort of the new kid on the block. So if you think that convolutional architectures were invented around 1990 and LSTM maybe 2000, attention is quite recent. Yeah, 2015, 2016. And yeah, we will see how it works in a moment. So the model sort of learns the alignment between different modalities. It can be applied to translation. So that's one of the main application areas, but attention is now being used in many applications beyond translation systems. Attention-based neural machine translation models are superior to non-attentional ones in many cases. For example, in translating names and handling long sequences. And maybe the first paper here is the second one by Badanao, Cho, and Benjo. So this is Joshua Benjo again. Neural machine translation by jointly learning to align and translate. And so in our discussion we follow this paper, if you want to read it up, by Chris Manning's team, Effective Approaches to Attention-Based Neural Machine Translation. So the attention layer sits sort of on top. So we have these blue boxes again and the red boxes. But now we have this attention layer. So we are calculating another layer of latent representations, which gives us these Z tilde layers, which then produce our prediction for the decoded words. And also, the hidden layer is fed as an input in the decoder, not the decoded word, which is also an interesting variant. Your E of S stands for end of sentence, and these are just stands for some words. A, B, C, D in one language, X, Y, Z in the other language. So maybe even the decoder has one word less than the encoder because languages are different. So the in the simplest version, we consider ZT to be a hidden layer of interest in the decoder, so on the right side, and ZT in this in connection with attention is called the query. Then we have CT, which is called context vector, and this attentional hidden state is then a sigmoid applied to a transformation on the ZT layer plus some weighted input from the context layer. So this is a matrix. It's a matrix. These are vectors. So we add something to this representation, and if we get the old model without the intention if all the D's are 0. Often people use a ton H instead of the sigmoid here. And then the word probabilities for the decoder are just the softmax of a weight vector applied to this Z tilde. So this is all happening here. So we have this, let's say this is the Z, and then we have here the Z tilde. And from here to here, this happens what I just described. We are adding something, and we have another connection here. We add something with this connection matrix D. And now the question, of course, is how this CT is defined. And then ZT is applied to give you the output. So you have another weight vector and then you get the Y's out. So essentially we are aligning in this approach a latent representation in the decoder with a latent representation in the encoder. No? So the problem which was addressed is that there's some language have different orders of words than other languages, and this can pose problems to simple encoder-decoder approaches because sort of this positional reference might be lost in this approach. So this, if this ZT was called the query, then this Z bar S, which is a latent representation in the encoder somewhere, no? So we don't say exactly where, could be anywhere, so this is called the key, and then we calculate the alignment. So how closely do they match essentially, no? And this is called AT of S. So the word at location T with any word in the encoder sequence, so the latent representation in the encoder sequence, we are calculating a score, which might be simply the inner product of these two vectors, and we put it in a softmax. No? So this is nothing but a softmax. So the what comes out is positive or non-negative and sums to 1. And this is what we call a line, and it sort of tells you how close these two latent vectors are. But they are, so score, the dot product is common, but there are other scores as well. And this context vector is then a weighted sum of the latent representations in the encoder. So that's this Z bar S. And it's weighted by the alignment. So this is essentially a weighted average of the Z the latent representations in the encoder, and so the ones which are similar to the one of interest, so the ZT, they get a higher weight in this averaging. And again, so this is just the point if you're a little bit scared that you're adding too much complexity here. If the model decides that all of this attention stuff is useless, it would just turn this D matrix to 0, and then we are back to the old encoder-decoder. And so this one idea is that if there's a word in the encoder which is related to a word in the decoder, and they might be in different positions, so the positions is sort of lost, which is intended. So a word in the encoder which seems to be similar to a word in the decoder, we can evaluate that independent of the location in the encoder. So here, here's a display. So here we have the encoder, and here we have this latent representation in the encoder. Here we have the decoder, and we are at some location ZT. Then we are calculating these align weights, and these are the weights with which we are calculating this weighted average of all these blue representations, which gives us the context vector, which is then added as an extra input and with extra weights to give this Z tilde T, which is then, and then there's another layer to the output. So it's, again, it's maybe a nice idea, but the most amazing thing is that it works very well, and there are even papers, there was a famous paper with the title "Attention is All You Need," which says, and we will come to this a little bit later, you might not need recurrent neural networks or convolutional layers at all. No? But here, I mean, these are still recurrent LSTM networks. So we have recurrency, we might not have convolutional layers here, but the recurrency is still there. But attention helps a lot. But then maybe you want to do a little bit encoding of the location in input space, and for that there are different ways you can do that. You can learn like an estimate of where the relevant word in the input sequence is. So you don't have just the alignment here. You also weigh it with a Gaussian window around some expected position in the input sequence. So PT is estimated in this way based on CT. So it gives you some hint if this word is expected to be in the center of the sentence, input sentence, or the end or in the beginning of the input sentence. So completely having independence of the location in the input sequence doesn't seem to be a good idea, and this local attention model helps you to encode the location of relevant word in the input sequence. So here this is indicated by this alignment position encoding, which tells you where the model expects that this relevant work was in the input sequence, but it can be this can be at the end of the decoder, and this could be at the beginning of the encoder. So you have still this flexibility. Yeah, so this is the architecture as I've shown before in a more abstracted way. So this attention is applied at any of these decoding steps here, and it sort of contributes information of the latent representations somewhere in the input sequence. So then people thought that this attention mechanism is such a great idea. Maybe we should not just apply it to encoder decoder problems, and we can apply it to the training of IID data, of sequential data, of anything we will maybe understand in a moment. So the idea is to have to deduce a variant of the hidden layer, which is a sigmoid applied to the normal hidden layer with some transfer function plus some contribution from the context vector. And the context vector is now not just applied to the encoder side, but to any instance of a neural network. So maybe let's first look at the graphics and then go back to the equations. So so these are different data points, and this is sort of the beginning of a deep neural network, let's say, or which can continue in the direction to the top. So in a normal feed-forward situation, we would apply the inputs here, train these layers, but the prediction of the hidden unit after training only depends on the input and the trained weights here. So you can think of them as words in a sentence, for example, but there could be anything. So one idea might be to say, okay, why not do a fully connected approach? Each hidden layer depends on all the inputs. Again, maybe these are words in a sentence, and maybe this latent representation here should get information on all the inputs. No? So this is rarely being done. It leads to overfitting and difficulty to generalization with sequences of different lengths, for example. Then here, this is the convolutional idea. Yes, you can get information from neighbors, if that's a sequence of words, but these connections, they should be shared. No? So the connection from here to here, this blue connection should be the same as the connection from this input to this hidden, and so on. And here the same symmetry. From this, if you shift to the right, then this shift should have the same weight vector, which essentially is this convolutional idea, and the straight one should also be shared. So everything is shared, and if these are sequences of words, then this can work quite well. So there are even some major commercial systems which work with convolutional approaches. The recurrent approach, LSTM or not, has this structure. So an input can produce an output, but it also influences the next hidden state, and then the next hidden state. And you have this architecture, and this can work quite well. I think in language models, most people would prefer a recurrent LSTM type structure, and convolutional approaches are a little bit less popular. And then we can have a bidirectional version where information flows in the forward direction and in the backward direction, and the decoder or the labeler can use both informations to provide optimal labels for a word, for example. Then here, this is the self-attention. So every network produces a latent representation vector, and then this context vector is formed where everybody contributes. So I don't draw these attention mechanisms here. And then this sort of refined latent representation is used as an additional input to the next hidden layer, which gets input from the input and from this sort of context vector. Yeah? So we have, and this the contribution to this latent representation here, and the definition of the context vector can again depend on different of all possible inputs in the previous layer. Of course, typically there's also some sharing of weights, which I didn't indicate here with a colorful display. Yeah, but the idea is that also an input vector, which might be further away, might have a significant contribution to a context vector, which then affects the refined latent representation here. Okay, so let's maybe go through the equations briefly. So in the feed-forward layer, for feed-forward architecture, the latent is essentially dependent. So we are assuming, so I didn't mention that, there are several layers of latent representations, and they have this index L for layer and L-1 for the previous layer. So we propagate weighted by V, and then applying the sigmoid to the next latent layer. And for this fully connected version, we get input from all the other previous layers, but this would be leads to overfitting. It is not being used, to my knowledge, but just as a principle. Then the convolutional layer does something similar, but these connection weights have a symmetry. So in this case, this sort of convolutional symmetry, that these weights are not completely independent, but they're all coupled as this convolutional structure, and this is quite successful in NLP applications. Then the recurrent architecture, where the next layer's latent representation depends on the previous layer weighted by V, and then you get input from the previous one, just from the previous hidden representation of the previous time step or index step, and this works quite well, in particular in form of LSTMs. And then we have this bidirectional equivalent, where we just allow propagation in the forward and backward direction, not just in training but also in inference. And then the self-attention has this context vector, where this D matrix is also learned, and we have this alignment vector, and the later representations from the neighboring or from the other instances. Yeah, we also compare it to, we have this graphical representation, where we have, in addition, a particular graphical structure indicating the neighborhood between nodes. So let's say we have three people, A, B, and C, three persons, and we know that A and B know each other. And I mean, there's always this concept of homophily, that people who are similar also are connected. So maybe the latent this mixture of this attention mechanisms should be limited to neighbors. And since we are applying or exploiting the graph structure in this sense, this is called graph attention network, because we have an attention mechanism here, but the attention only works for neighbors to which a node is connected. So person C is not connected to A and B, so we don't see this attention mechanism. It sort of works on its own, but since A and B are connected, the attention mechanism is applied here. And there's you can also think of this as a recurrent neural network propagating forward in time. Then you get the recurrent graph attention network, where you have an attention mechanisms between neighbors, but now this propagation here is thought to be propagation in time, and at each layer you can get context vectors which are composed from the latent representations of neighboring units. This is quite sophisticated, and maybe it's too short to completely understand it here, but the idea is to include, to have this attention mechanism, but only between nodes or instances which have some sort of connection pattern. And so this could be, let's say here on the left side, maybe patient A and B are very similar in ways which are not represented as inputs to the neural network, and C is very different. Then maybe A and B can share sort of information or statistical strengths by this type of coupling. So this is called a GAT, or graph attention network, which is an example of a graph neural network. And graph neural networks are currently extremely exciting, and a lot of interesting work is happening there. And we show how we relate it to combine it with the attention mechanism. So in conclusion, sequential models find many applications, for example, in natural language processing applications, including machine translation. And attention mechanisms are the basis for state-of-the-art machine translation systems, like the transformer, which is extremely hot thing, and a lot of research is being done with the transformer. And context-sensitive embedding models, So we talked about that we can pre-train models, language models and other models to learn these embedding vectors. But these embedding vectors would be sort of static, and wouldn't consider the context of the word. And BERT is a very powerful approach to include these context informations in the. So an embedding of a word also considers the context of the word, and it uses self-supervised learning in a pretty sophisticated way. Okay, finally, I want to talk a little bit about the transformer. So it's definitely outside of the topic of the lecture. It is complex and would probably require a whole lecture on its own. But we went all the way to self-attention, and the sort of the ultimate model, which is quite successfully used in many applications, is the transformer, which is the next step. It essentially adds a lot of complicated things, but it uses the attention mechanism, and so I thought I added at least as an appendix. So the transformer dispenses the recurrency and the convolutions. So in the encoder-decoder system, also with attention, we still had an LSTM structure which produced the latent vectors. And the transformer goes a step further, as we discussed in the context of self-attention. So it removes also the recurrency in the encoder and the decoder. And it's completely relying on attention mechanisms. So each layer has two sublayers comprising multi-head attention layers, followed by a position-wise feed-forward network. First we consider self-attention again, but we are introducing a lot of matrices to make it more flexible. Before, the alignment was sort of a softmax applied to an inner product. Now this might still be an inner product, but we also introduce these additional transformation matrices or weight matrices. WQ for the query, WK for the key, and WV for the value. So now essentially we have a more complex context vector, more complex and more flexible, because we can learn these additional parameters. But not only that, we learn several of these mechanisms, of these context vectors. Because we define an index from 1 to R, and for each of these indices we can learn different W matrices. So the W matrix now also gets an index K. So we don't just produce one context vector, but we produce R of them, and in this context they are called heads. And Then there is the context vector overall is then first you concatenate all these heads. No? So these are heads concatenated, and then we apply another transformation matrix to this to give us the final context vector. So we make the context more flexible. We allow for different weighting or combination matrices W, and we allow R of them, and then we have a way of combining them. So it's called a multi-head attention because we have multiple heads, and this is quite a big matrix, the WO matrix. Then they also introduce a simple feed-forward network for the combination. So here we consider we calculate this X vector as this weighted combination of the Z layer and the context vector, and then we apply sort of a transformation where we learn the difference, which looks a little bit like a ResNet sort of thing. So there are a lot of details which are complicated, which in detail would take a long time to explain. I want to give you a little bit the flavor of what's going on, because as I said, we would need to spend much more time on this detailed architecture, and it's not clear that we really get a lot of insight. In training, masking operations are being used to hide the downstream target words. So that's a form of self-supervised learning. It adds another normalization layer, the layer normalization, which is related to batch normalization. It uses positional encoding. Again, we don't want to be completely independent of the location of the word in the sequence. So this is done by positional encoding. For example, bird, which is not the transformer, but it's also uses self-attention, so it would not be able to distinguish between live to work and work to live, which has a very different meaning, of course, these two sentences, whereas LSTM would be able to do that because it's a recurrent structure, so it would have different representations here. And to introduce that, we also use positional encoding in the encoding side. So this is how it looks on the encoding side. So we have these word representations. We have self-attention layers, then the normalization and the addition, then feed-forward structures here, then another add and normalize concept here, and then maybe we have another layer of all of this, self-attention, add and normalize, and feed-forward. Then add and normalize, and this is then the vector which is transported to the decoder, and the decoder is similar to the encoder but uses two more layers. I'm not sure if we have to go through the details here, but it also uses multi-head attention, and the information from the encoder enters here in different locational positions, and we have the different layers of self-attention and normalization layers and feed-forward networks, and as I said, we don't have enough time to explain in detail. I just want to give you a flavor and show you the relevance of these attention mechanisms and self-attention mechanisms, and they are sort of the cutting edge today. These architectures and the best translation models and the best models for word understanding, text understanding are based on this idea of attention and self-attention in some complex architectures. This is how it looks like when you combine these two things. Yeah, so BERT, I mentioned before, stands for Bidirectional Encoder Representations from Transformers. From Google, leverages attention mechanisms and transformer to learn word contextual relations using a masked language model. Elmo is an approach for embeddings from language models, from AI, so to AI, or AI squared, I think it's called. And GPT, generative pre-trained transformer from OpenAI, produces a lot of news and attention because it's also used as a question answering system. And a lot of people use it and abuse it. And Albert is a light bird for self-supervised learning of language representations, also from Google. So some people work with Albert if they cannot afford to work with these huge models like BERT or other similar models. So yeah, so I guess we had a long path today from a time series prediction type of applications to sequence modeling, to recurrent neural networks, then LSTMs, then the attention encoder-decoder architectures in language, then the attention mechanism, and hopefully that can all be understood from my presentation and my slides, and maybe you also understand the logic behind these approaches and why they're used, and so I just the transformer is definitely something outside of the lecture, but since we went so far, I thought I'd give you some intuition and some insight how it's used in the transformer context. But attention is used also outside of the transformer and is surprisingly effective in many applications, and in particular if convolutional networks and recurrent neural networks might be not applicable, like in graph structures, the attention mechanism can give you very good results. Okay, thank you very much for your attention.